All right, sorry about that. So we were looking at the acceleration and motion of trains, okay? And so let me go ahead and repeat this last part that we were trying to figure out. So we're trying to figure out the final angular velocity of the wheels and the linear velocity. So let's go ahead and look at our equations, okay? And we want to know omega, so these two equations would be good to look at, okay? We have our alpha and we have theta. So why don't we go ahead and use this equation here since we don't know a time. Okay, so we're going to say omega squared equals omega naught squared plus 2 alpha theta. Okay, so omega squared equals omega naught squared plus 2 alpha theta. Okay? Alright, so let's see, we have this value and we started at 0. Okay, it started from rest, so that's going to be our omega naught is 0. Okay, so then we have omega equals 2 alpha theta, and then square root that. Okay, so we can plug everything in. 0.250 radians per second squared times our theta, which is 200 revolutions times 2 pi radians over 1 revolution. Remember, we need to be consistent with our units, and then take the square root of that, and that will give you your angular velocity. So let's plug that into the calculator real quick. And I get 25.1. And we can go ahead and look at our units, make sure they're correct, and they are radians per second. Okay. Oh, whoops. Oh no. So I'm trying to learn how to scroll, and it really does not like that. Oh. Okay. So the last part is what's the linear velocity of the train? Okay. So let me go ahead and look back here. Let's see. I think we did this earlier. Yes, okay. So here is my linear velocity in relation to angular velocity. Okay, so V equals R omega. Okay. So V equals R times omega. So R is 0.35 meters, and omega we just solved for is 25.1 radians per second. Okay, we plug that into our calculator. We get 8.77 meters per second. Okay, so this is my linear velocity. This was my angular velocity. So linear velocity and angular. Okay. All right. Let me see what other. Okay, yeah. I need to also do one more of these. One more. Okay. It does not like me. Okay. Whew. This is rough. Okay. Just because I'm having a hard time. Oh. Okay, the more you know. So now I know how to do that. Okay. Example 10.6, we're looking at a microwave. So it says a person decides to microwave to reheat some lunch, and in the process, a fly accidentally lands into the microwave and is on the outer edge of the rotating plate and remains there. And if the plate has a radius r of 0.15 meters and rotates at 6.0 RPM, which is like our angular velocity, calculate the total distance traveled by the fly during a 2-minute cooking period. Okay, so we are cooking a fly. Okay, let's go ahead and do some unit conversions first, and then we can determine that distance. Okay. So, there's 60 seconds in a minute. Well, actually, this is rotations per minute, so that might actually be okay. Total distance, so one rotation, or one revolution, is 2 pi radians. So let's go ahead and convert that at least. 6.0 revolutions per minute. 2 pi radians for one revolution. So 6 times 2 pi, 37.7 radians per minute. Okay. And so again, we're looking for the total distance traveled. So distance traveled. So let me go to our kinematic equations here. Okay. So we can figure out, let's see, we have a time, we have a velocity, okay, so we have a velocity, we have a time, we don't have an acceleration. That's all we have time and velocity. So we could figure out the amount of times it's rotated and then go from there and solve this way. I think that's what we should do. Okay, so use this first equation, and then from there solve it with this equation. Okay, so theta is going to equal omega times t. Okay, so our omega is 37.7 radians per minute. Our time is 2 minutes. Okay, so we can multiply that by 2. So we get 75.4 radians that it travels. And then our distance travel x is going to be r times theta, which is going to be 0.15 meters times 75.4 radians. Oops. That tells us that it's going to be 11.3 meters that this fly travels. Okay. This is kind of a silly example, but it works. Okay. All right, so let's go back to our PowerPoint now and continue. Now we want to start talking about another quantity called rotational inertia. Okay, so I'm going to go ahead and do this step by step in explanation. So we start with Newton's second law, okay, which states that F, or force, equals mass times acceleration. F equals ma. okay? And what we say is we can also state this in rotational sense, where our acceleration is equal to r times alpha, okay? So this is going to be our acceleration, but now we're going to put it in terms of rotation, okay? So this tells us that our force, we can still calculate it, but it's now going to be mass times radius times alpha, or our angular acceleration, okay? Now we can multiply both sides, so we're multiply by r on both sides, okay, of this equation, or I'm sorry, really of the one above, okay? And we will now call this our torque, T, okay? So this is a new quantity, torque, okay? Now, our rotational inertia, or moment of inertia, of a point mass m at a distance r from the center of rotation is this quantity here, m times r squared, okay? So, again, we started with Newton's second law, okay? F equals mass times acceleration. Put that in terms of, rotation. We just multiplied by r and then said that that is equal to torque, okay? So that's what this T is. It's called torque, okay? It's actually a tau, okay? So we have now said that tau, or torque, equals both radius times a force and mr squared times alpha, okay? We can also say that it is equal to some inertia times alpha. Whoops, okay? So again, rotational inertia, or moment of inertia, of a point mass, say like here on this table, at a distance r from the center of rotation is going to be mr squared. So inertia equals mr squared in this basic sense. Okay, that's for a circular path. So we're assuming that this mass rotates along that circle, okay, that circular path, given some force and mass and a radius, okay? One thing to note is that our force is going to be perpendicular to our radius always along this line, okay? So just keep this in mind, okay? Just in a directional sense. Now, rotational inertia is basically Newton's second law for rotation, okay? So we have, again, our torque, net torque, is equal to I, or inertia, times alpha, okay? And here are some different instances, some different systems, okay, that you can describe inertia, okay? So say this one, a hoop about cylinder axis, is inertia is going to be its mass times its radius squared, okay? But then if you go to a solid cylinder, whoops, it's going to be mr squared over 2, and so forth, okay? So whatever shape you are observing or looking at, okay, you want to make sure that you are using the right inertial equation, okay? So from here, we are going to go ahead and do an example. My time is running up, so I will do that in the next video.